Yeah, I'm ready.
All right, ladies and gentlemen, if we could please take our seats. Would love to continue with the program. All right, so our next speaker actually completed his undergraduate degree in information technology at RAU, which is now known as UJ, in 2003, followed directly by an honors degree in computer science. He worked in the United Kingdom writing psychometric software for Scitech International and returned to UJ to complete his MSc in computer science in 2009, followed by his PhD in 2014. His research interests focus on the application of the principles of biologically inspired intelligence to the development of multi-agent systems. He's currently the deputy head of department in computer science at the Academy of Computer Science and Software Engineering in the Faculty of Science. Ladies and gentlemen, here to speak to us this morning on biologically inspired multi-agent intelligence, please help me welcome Professor Duncan Coulter.
Hello, thank you very much for attending, and greetings to all of those watching via the internet. I'm currently in the grips of a migraine, so I'll try not to let that interfere with my delivery of the contents, and if it does do so, I apologize, but we should be able to continue. So as mentioned, my research interest is biologically inspired multi-agent intelligence, sort of a subfield within AI, which is a very broad blanket term that covers a wide variety of disciplines, and as mentioned by the keynote speaker, is one of the components in the fourth industrial revolution. So biologically inspired multi-agent intelligence, it's an approach to creating intelligent systems, which aims to model that approach by studying the existing examples of naturally occurring intelligence. And there's just so many things wrong with this high-level definition that I've given you, so we'll just need to unpack exactly what's wrong with that idea and how we can make it less wrong. So, firstly, biologically inspired. The bio in biological is obviously refers to life. So, what on earth is life? That's a great question and open for a lot of philosophical interpretation. It would be probably foolish to assume that life is something that just occurs with DNA or chemistry that's similar to ours. So, there could be life based on other kinds of chemistry or other processes, or indeed purely digital life. All of that is within the realm of possibility. So you could take a very abstract, high-level look at what life is as some sort of a process that attempts to lower its local entropy, so keep things ordered for itself at the expense of exporting disorder or entropy into the environment around it, and also then tries to replicate itself so that there's more copies of itself going around. That definition should apply to digital as well as stranger chemistries, as well as other processes that could be considered life or lifelike. So that's the biological part of it. But what is inspiration? So biologically inspired computation, what is inspiration? Well, human beings are amazing, and they're able to take a look at a complex process in the world and extract the key features, the salient features of that process, and attempt to replicate that somewhere else. So for ages, we've wanted to do various things that our biological history didn't allow us to do. So, for example, human beings have wanted to fly ever since we've seen other animals do it that we can't. And so we've taken our inspiration sometimes from what we see in nature in terms of creating devices and artifacts and approaches to doing the thing we want. For example, we've been doing for ages, as mentioned, so Leonardo da Vinci has many diagrams for various flying contraptions, some of which are similar in ways to approaches we use, and some of which are quite different. And throughout history, we've been trying to draw our inspiration from nature. Now, there's a good question. How much must you copy to be inspired, and how much must you abstract and refine and do your own approach to creating something rather than just blatantly copying something from the environment? So if we were to let's see if I can launch this from within the blindly copy flight as it's done by birds, for example, and try and build a machine that way, it doesn't work that well. Planes don't work on the same principles that birds do. helicopters definitely don't work on the same principle that anything in nature works on. So our attempts to blindly copy things from nature will result in various failures. So we have to moderate our attempts to copy. So that's the inspired portion of the topic. And then we ask ourselves, well, what is artificial intelligence? Again, a great question. So various thinkers have proposed definitions for artificial intelligence, such as Alan Turing, who's very well known for his Turing test, which is very much like about human style intelligence, with the idea being that if you can create a system that's able to fool people into believing that it's intelligent, you should consider it to be intelligent, which is quite reasonable because, I mean, if you look deeply at the philosophy, you don't know that anything else exists apart from yourself. That's sort of the starting point of philosophical discussions about the nature of being, solipsism, where basically you are the only thing that exists, but that's a lonely way of viewing the world and often sort of seen as the sort of absurd reduction of some philosophical systems. So you obviously interact with what you perceive to be the environment, and you interact with entities that you experience in the environment. And if they seem intelligent to you, other people, you treat them as though they were intelligent. That's called the polite convention. So all that Alan Turing really did was he extended the polite convention to systems that weren't human beings. However, this is not a wildly useful view of artificial intelligence because typically throughout the history of artificial intelligence there's been two schools. There's been the attempt to create strong artificial intelligence, which is human-like and borders on other related concepts like artificial consciousness, and then there's been the soft, weak artificial intelligence, which is surprisingly much more useful, to be perfectly honest, because you don't necessarily want to create self-aware, conscious entities. You want to extract the useful properties of intelligence to improve the well-being of human beings, including yourself. So, very well-known Dutch computer scientist Dijkstra, whose algorithms power the routing of information on the internet and has made very important contributions to programming and software engineering over the years, posed the question of whether machines can think is about as relevant as asking the question of whether submarines can swim. They don't. They move through the water. They do it in their own way. Of course, that being said, not all submarines do their job equally well, so you can wind up with artifacts that aren't doing the job that they're meant to do. And that's my personal view of artificial intelligence. It's embedding the intrinsic properties of intelligence into an artifact rather than creating intelligence out of nothing, as it were. So overall, we'll take a look at biologically inspired AI from a sort of bottom-up approach, and we'll follow the sort of template sets forward in nature. At the lowest level, we've got some sort of chemical reactions going on that makes biology biology. Those fundamentally are built on things that can replicate themselves, and then those replications are imperfect. So the imperfections mean that some perform better than others, and the environment that they're in will favor those that perform better at replicating. So an evolutionary pressure is placed on those replicators. Eventually, they reach some sort of level of complexity where you can start to view them as organisms. So we'll take a look at some organisms in nature which are intelligent, but in ways that are entirely unlike how humans are intelligent. As I said, my focus really isn't mainly on replicating human intelligence, but on analyzing and capturing the essential qualities of intelligent systems and seeing if they can be applied in the development of software systems. So some of the simplest organisms that exist display remarkable amounts of intelligent behavior. For example, slime molds. We'll take a look at, within an organism that we do consider to be intelligent, like a human being, how its different cells cooperate to work with information through neural networks. And then we'll take a look at another process or aspect of, say, of vertebrates and higher animals and so on, that is also could be considered intelligent, and that's the immune system, which is able to respond meaningfully to a wide variety of things that could cause harm, pathogens, that it could not possibly have seen before, and it must then perform better in the future, having learned something about the nature of the pathogen that it was exposed to. Once you've got organisms, the next level up is organisms cooperating with each other. And that brings in the multi-agent aspect of my research. An agent is basically, well, we'll discuss it in more detail, but it's an entity that can have some degree of autonomy. And interesting things happen when such entities interact with each other. So we'll take a look at uh, other non-human intelligences in the form of social insect swarms, things like ants and bees and all sorts of things are able to cooperate and create a collective that behaves more intelligently than any of the individuals could, in the same way that a neuron is not intelligent, but the collection of neurons certainly is. So somewhere through the interactions of those components, there's an emergence of this property of intelligence. A lot of things in reality aren't properties of the individual components. I mean, science is built on a reductionist approach, and that makes sense, but sometimes you can't see the properties, the bulk properties of systems that emerge when they act together, which is quite interesting. We'll also take a look at flock and shoal formation. So birds and schools of fish are able to behave collectively as a single entity to reduce their threat to them from predation, and it creates these very beautiful visual effects. And then cultural evolution and so on. How these systems evolve over time. So if we take a look at the smallest level, we've got these ideas of replicators that exist in biology in the form of various things like DNA and RNA that are able to be copied. But if you look at it mathematically, you can view these things very, very simply. So there's a great little mathematical game, although it's a zero-player game, so there's no actual winner or loser or anything. But it's a system. It's what we call a cellular automaton, basically a grid where cells are either considered to be alive or dead. And by applying very, very, very simple rules, we are able to view complex emergent behavior by watching these rules play out. So the rules basically are, if we take a look at any particular cell, if that cell is alive, so live cells are represented by a black square, then we count the neighbors around it. Well, we do it for all cells, alive and dead. And then the basic idea is if there's more than 3 neighbors, then the cell is overpopulated and dies. If there's 2 to 3 inclusive, then it stays alive. And if there's less than 2 neighbors, it dies of, let's say, loneliness. Whereas if it was a dead cell and the total count of neighbors was 3, then it springs into life through reproduction, if you want to view it like that. So a really simple set of rules by John Conway. And as we can see, these... oh, it's not, doesn't come out so well in the contrast there, but the next still image, you'll maybe be able to see it better. You're able to get these fairly complicated patterns that emerge if your starting conditions are correct. In fact, a cellular automaton is what we call, in the class of automata, it's one that's capable of universal computation. You're able to build machines simply by setting the starting live cells before running the simulation that are able to carry out the basic processes of computation. So anything that could be computed by a physical computer could be computed in simulation by Conway's game of life. It wouldn't be efficient, but the point is that these rules are ridiculously simple, and from those very simple rules can come anything, complexity equal to any algorithm that you could express in any other programming language. You can also make these cellular automata very, very simple, one-dimensional. So if you look at each of those images there, it's a one-dimensional world instead of a two-dimensional world, where you only consider your immediate neighbors and then evolve the system with time going down. I think that's not terribly interesting. These are what we call elementary cellular automata. But it turns out that by adjusting the rules slightly and then keeping a history of the previous state, so basically each row in these images is built up from applying the rule, storing the old state, and moving on to a new one, you can build up fairly complicated images. Most of the rules collapse into chaos or nothing. Some of them create very fixed, rigid patterns, and some of them create very interesting patterns that are sort of on the border between chaos and order. And it's those class 4, what they call elementary cellular automata, which are very interesting because that boundary between chaos and order is where a lot of complexity can be found. In fact, these class 4 cellular automata are what Stephen Wolfram, the person who studied them in a lot of detail, calls irreducibly complex. There's no way to get to one of the final states than by doing any less work than running that computation every step of the way. So it's quite interesting. And you may notice, if you're mathematically inclined, that some of the ones shown here look a bit like, say, for example, the Sierpinski triangle, which is a well-known fractal pattern. I've used these in my research to help agents coordinate in a dynamic way, basically by their neighbors, the other agents that they're able to reach, is built on a cellular automata based system that changes over time, which means that the community of those agents fluctuates over time. The idea being to sort of preserve complexity going forward. The next slide is not that easy to read, but basically it's evaluating all 256 elementary cellular automata rules as the basis for this cooperating neighborhood. And what it basically shows is that some rules are really, 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 really good at preserving this useful cooperation, and others are just garbage. And the rules that happen to be very good at preserving